Returning from a function call means ending the function call and determining what is the value of the call expression. So return statements we've seen, but we haven't talked a lot about. A return statement is there to complete the evaluation of a call expression. When you evaluate a call expression for a user-defined function, you have to execute the body of that function in a new environment, and you keep doing that until you reach a return statement, or you reach the end of the body. So, when you reach a call expression like f of x for some user-defined function f, that's when you switch to a new environment, and it's time to execute f's body. Why are we doing all this work? In order to figure out what's the value of f of x. When the return statement within f is reached, we switch back to the previous environment, the one in which f of x was being evaluated, and now f of x has a value, and that value typically determines what happens next in the original expression. We're maybe assigning the value of f of x to a name, or passing it in as an argument to some other function. Whatever it is, when we reach the return statement, f of x now has a value, and that value is the value of the return expression in that statement. Only one return statement is ever executed while executing the body of a function. Once that return is reached, we're done. So for example, let's write a function that prints the final digits of an integer n in reverse order until d is found. And let's assume n is non-negative. Here's an example of what we're doing. End of 3, 4, 5, 6, 7 is all the digits starting from the end of 3, 4, 5, 6, 7 until we reach a 5, and then we're done. So we start with 7, and then 6, and then 5. We found a 5, so we're done. How would we write this function? Well, one simple way to do it is to write a while statement that just prints all of the digits, 7, 6, 5, 4, 3. The approach here is to say that while n is greater than 0, we split n up into its last digit and everything but the last digit, print the last one out. Now we need to make sure that when d is found, we're done, and we can do that with a conditional statement containing a return statement. If I find d as the last digit in whatever piece of n we're currently looking at, then we return none as a way of ending the process of the while statement. Once you return, nothing else gets executed within the body of this function end. Let's look at some more examples of when we might return from within the suite of a while statement. I'm going to write a function, search, which is a higher order function. It takes another f, and it keeps trying all of the integers starting at 0 and working its way up until it finds one for which f of x is a true value. Now, what's a true value? True is a true value, or a number that's not 0 is a true value. So we'll start with x equals 0, and I want to keep trying x's just as long as it takes to find one where f of x is a true value. One way to do that is to purposefully construct an infinite loop. This while statement will run forever unless a return statement within it tells us that we're done. While true, if it's the case that f of x is a true value, I want to return x. If that's not the case, I want to try a different x. I could write this as x equals x plus 1, or the shorthand x plus equals 1, which will have the same effect if x is a number. Here's a simple function to search called is3, which will return true just when x equals 3. Putting these together interactively, we can see what happens. I want to search for an x such that when I pass it into is3, I get a true value. And that's because when I call it is3, on 3, I got true, but when I called it on 2, I got it a false, 1, I got it on a false, etc. So far, this brute force search seems pretty useless, but let's get a more complicated example. Here's the square function. Here's a version of the square function that is always non-negative because it takes a max of 0, and then we'll square x and subtract 100. So this positive function, when I pass in 2, I get 0, and 3, I get 0, and 4, I get 0, and 10, I get 0, because x squared minus 100 is 0. But if I pass an 11, I'll get 21, because 121 is the square of 11. So the goal of search is to find the smallest number x for which x gave a positive value. Now there were no trues and falses here or comparisons. We're just using the fact that 0 is a false value and that any other number is a true value in order to reach this return statement. And what's cool here is that 11 is related to the square root of 100. So far we've come up with a scheme for finding a number that's one more than the square root of whatever I put there. A method for computing square roots just by trying a bunch of numbers until I find it. This is a general strategy for computing inverse functions. The inverse of s is to return a g such that it's the case that f of x passed into g gives us back x. And how do we find such a g? Well, it's a function that takes in y, and then we'll just search for an x that satisfies f of x equals y. So notice the square root is not built into Python, but I can define it now by saying it's the inverse of square. Now, just like I can square 16 to get 256, I can take the square root of 256 to get 16 back. Or the square root of 16 is 4, and the square root of 4 is 2. Now this version of square root will only work for perfect squares. Right now it's searching for an integer that when you square it gives you 2, and there is no such integer. So it's not the most ideal implementation of square root. If you want to see a better version, take a look at the Newton's method section of the textbook. But for perfect squares, it works just fine, and it's pretty simple. As a final question, is there a way to write an even shorter version of search? Well, sure, I could say, well, it's not the case that f of x is a true value. I want to add 1, and then I want to return x once I've found a true f of x. And this version also allows us to compute square roots, just like before. So I think once you've written down an implementation for a function, it can't hurt to stare at it for a little while and see if there's some way to simplify the logic.